Hello everyone, my name is Noah Gartini and this is my submission for the R application assignment for MSA 8310. Please be lenient with me or forgiving. This is my first attempt at making a video, a video tutorial, so please be awesome, just like the name of this package that I chose. So I chose XGBoost, which is Extreme Gradient Boosting. It is the reason why I chose this application is because oftentimes I'm faced with a problem where I need to classify something, or I have to classify a value, or I have to find out like the factors that are important for making a certain decision. So I can use it for either prediction or for learning more about why certain things happen. And then with the cool thing about this one is that it actually helps me. It's actually pretty easy to use. The feature engineering is actually the most difficult part. I'm going to breeze through that section of it, but the code is available if you guys decide you want to take a look at it. Gradient boosting is different than a decision tree or a regular classification model, because what it does is it'll not only just run the model once, it'll run it as many times as you tell it to. And then each time it runs the model, it'll learn from itself, and then it'll slowly get closer and remove the amount of error that you have from the prediction. So that's actually pretty cool in and of itself, is that this is an actual machine learning application for R. So yeah, let's dig straight into the data. So the classification that I decided to do here for this one is I wanted to predict. So I took data from Kaggle, took a Google Play Store apps, and then I created a dummy variable, which is a binary variable for the number of installs that there are. So anything that's over 100 million installs is a 1. Anything below 100 million is a 0. So I want to understand what types of things within this data set would contribute to someone downloading, someone installing an app, or over 100 million people installing this app. So this data set is actually comprised of two different tables. There's a Google Play Store.csv and Google Play Store user reviews, which I actually ended up using both of them. I had to do a pivot table for the user reviews based off of the different apps, and then find the median sentiment polarity as well as the sentiment subjectivity. And then from there, I joined it back into this table over here at the app level, which is in order to get the rest of this data over here. So a brief overview of what that looked like, what that process looked like. So this is the raw table. We have sentiment polarity, and sentiment subjectivity, and then broke that up again into the pivot table for each one of these, and then took the App Store raw table, and then pivoted it and to remove some deduplication. And then from there, we also, to remove some duplication, and then from there, I rejoined it back. I rejoined the app review data back to the Play Store raw data that I went through and I cleansed. And I added in my dummy variable over here, my binary value for over 100 million installs. So we have a category, which is the category of the app. We have whether or not it's free or it's paid. We have the size in megabytes. Do we have the price? Most of them are free, as you will notice. And then we have the number of installs. This column is actually going to be removed because it gives too much information about the label, about what we're trying to predict. So that's actually going to be dropped later on, and we have an R script to do that. We also have the rating in terms of from 1 to 5. We have the content rating, so whether or not it's for everyone, if it's mature, if it's teen, so on and so forth. It's like your rated R movies and so on and so forth. You also have the Android. We also have the Android genre. So the type of app that it is. This is duplicative. It's just a subcategory for this one. That's actually going to be dropped as well, because it's redundant information. We also have the current version of the app. We also have the version of Android that the user is running. We have the sentiment polarity, and we have the sentiment subjectivity, and then the max number of reviews that had, and then the number of reviews that the app had in the App Store at the time of the data being scraped. So some descriptive variables about this. So how many 100 million plus installs per category? As you'll see over here, we have games, taking the top, taking the cake, which is at 22. We also have family at 9, tying in with tools at 9, and then communication at the close third at 7th. But there is a huge disparity over here. So I have a feeling the category is going to be a huge factor in this. It's going to have some sway on the decision for the decision trees. We also have sentiment subjectivity versus sentiment polarity. So just wanted to see how many apps actually had good or where they laid in terms of like how subjective their reviews were by the users, like basically how on task the users were whenever they were writing the reviews, if they were just talking about something tangentially related. And then also the polarity of them. So whether or not they're positive, which is would be on the right of the 0, and then left, which would be over here. So these would be negative and these would be positive. So I did search these values up later on, but essentially these which are the high subjectivity and the high positive polarity. These ones were actually tool applications. So people found something extremely useful and extremely helpful. And then they were very specific about the type of app that they were using and everything in there. So it was right on task. These are the types of reviews that you would ask for. Everything else over here would range anywhere from, it was good to I like apps. And then that's pretty much that. So we'll see over here that maybe positive polarity might have something to do with it, as well as subjectivity might have something to do with it, might be an important feature here. We also have free and paid, so just broken up by the binary value. So we notice over here that the majority of the lion's share of the apps are actually free. There's only a handful of paid apps, and then we also know that seeing that there's only 10% of I did the math. This is only about 10% of the total population of the total apps have over 100 million installs. So this is a particularly rare event in the data set. We also have that broken out by content rating. So we have over here, we have 62 installs for everyone rated games. We also have 15 apps that were installed over 100 million times. And then we also have the median of review numbers by rating. So we notice over here that the majority of the ratings were actually happening over here in the 4.6 range, by quite a margin. So there are a lot of apps here that are rated pretty high. The majority of them are above 4. So that means that there's not very many. There's a lot of good apps in this data set. So that should be something to keep in mind. And then without further ado, let's jump straight into the R script. So want to set the path. We're setting the path. We have install packages over here, XGBoost, tidyverse, and diagrammer. But you don't have to install that multiple times. You just have to do it the first time. Library XGBoost and library of tidyverse. Then we have the Playstore info, which is our data. We're going to set a random seed. We're going to shuffle the data around. Then we're going to take a quick look. It looks exactly like it did in the G sheet that I just showed you. And then the next step that actually happens is the feature engineering. So I'm actually not going to go over the steps just for the sake of time, but I'm going to talk about what each one of these steps are and why we need to do it. So the convert target variable over 100 million installs. So XGBoost only knows how to do things with Boolean whenever it uses a label. It has to be true or false. It can't be 0 or 1. It cannot be a binary value. So we're going to go ahead and do that here. So the only difference here is you have 1s and 0s versus true and falses, which is what XGBoost likes. And then item number 2 is to remove the features that we don't want. So we're actually going to get rid of that installs that I mentioned earlier. So we're going to go ahead and do that. And then the next step is to split the numerical from the categorical variables. So the reason why we do that is because we're actually because XGBoost doesn't know what to do with categorical variables. Everything needs to be numeric. So we're going to split that up. I'm going to check the work. Everything looks good. It's all numerical. After that, we're actually going to take all the categorical variables and we're going to turn them into a hot matrix. So it has to be binary 1s or 0s or dummy variables, whatever you want to call them. So we have the 5 categorical variables that we're going to turn into dummy variables. So 1, 2, 3, 4, 5 for the category, content rating, type, version, device version. And then after that, we're gonna merge all of them back into one data frame, and then convert that into DMA into a matrix. Then after that, we're going to split the data set into testing and training subsets, which is very important. So this function over here actually takes all the samples, and then it divides. Then it just assigns. It tags 70% of them at random. So we're going to go ahead and do that, because we're going to do a 70-30 split between the training and test. And then we're going to create the training data set. This is going to take those 70% tagged rows, and it's just going to turn that into the training set. I'm just going to take the remaining 30% over here and going to make the test set. The next step over here is to take those training and test sets and actually convert them into D matrices. The reason why it's important to do it into this particular type of format, object type, is because XGBoost only knows how to work with D matrix, does not know how to work with a data frame like other ML applications do. So without further ado, we have a clean data set. Let's begin modeling. So from here we have very basic model. The only thing that we really have called out over here is how many boosting iterations we're going to have, and then also the objective, which is a binary logistic. So we're classifying whether or not something is going to be a 1 or a 0 for 100 million plus rows based off of the rest of the data that we have. So we do that. We run the model. If you notice over here, we have two rows of training errors, which is pretty much what we have over here, which is equal to 2. And then that'll increase as you increase the numbers that you have. We have some future versions with that tweaked a little bit further. So the next step is to generate the predictions for our held out testing data. So we're just rerunning the model with the test data. We're calculating the errors, and then from there we're doing a test error. So this will calculate the error between the two, between the test data and the training data. So right now we're at a 5.4% error between the training and the sample. Between the training and the testing set, which is good. That means it's not completely overfit. So the next step over here is to do a model tuning basics, and that's to increase the max tree depth. So that'll increase the number of leaves, or the number of times that the tree will split. So that's important. You don't want to have that too high or too low, because then you'll either over or under fit the model. So you'll either get super specific with the things, or you'll be very vague and very general with the decisions that the model makes. And it's completely dependent on the type of data that you have, how wide it is, how long it is, how many rows you have, and how deep you want to go into it. So without further ado, we'll go ahead and do that. So we'll just train another model. Again, it produced 2 values. If you notice, there's actually 2 different values over here. On the second iteration, it looked like it actually increased the amount of error from the training set. But if we run the model the model generated, the model tuned on the test set, and we calculate the error and we print it, we see that it actually less than the test error is actually reduced. So now we have a 4.6% error. So it dropped about, what was that, like some number below. The next step over here is actually model tuning advanced, weighting rare events plus early stopping. We have get number of negative positive cases in our data. So the reason why we're doing this is because we have a particularly rare event, and we want to do some weighting to score the positive instances more higher than the rest of it. So basically, because we have such a low number of instances where there's over 100 million installs, we want to weight for that, and we want to compensate for that in the model. So we're going to take all the trues and the falses for the negative cases, and we're going to tune it. The main difference that we're doing over here is we're actually including the scale position weight, and then we're calculating that as the percentage of negative over positive cases. So we're just overcompensating for it. And then the other thing over here is the early stopping rounds. So this will basically run the model 10 times, but if it notices that after 3 times is not a significant difference between the two, then it'll just drop it. It'll stop the model. It'll keep it from running all those 10 steps, which is good if you have, if you are early on and you're just going like, I'm just going to throw everything at it. I'm going to break my computer. I want to hear it wheeze. Then you can set that to 100. But if you want to make it stop at like 5, just so that it stops it from doing that unnecessarily, then you can do that. So negative, positive. We tune it. We ran it. So we ran it. We had it set to end round equals 10. So as you can see over here, we have 10 iterations over here. And it'll tell you it will train until error hasn't improved in 3 rounds. So that's basically just saying that early stopping rounds is equals 3. So if you, as you notice, the error did get smaller over time, which is a good sign. So we'll go ahead and we'll run the prediction against the test data. We'll calculate the error. We'll print the results. And we'll notice that the error actually did worse than whenever we had a smaller number of iterations. So it started off at 4.6%, and then we ended up, after we added all those tuning parameters, into 7.3% or 7.4%, which isn't necessarily that good. So after that, we're going to be adding a gamma regularization, which I'm not too familiar with the math on this, but essentially what it'll do is it's the larger the value, the more strict it is. So I'm going to read something from a site that I found. So the higher the gamma is, the higher the regularization. Default value is 0, which means no regularization. So gamma values around 20 are extremely high. It should be used only when you're using a high depth overfitting, where basically when you're overfitting really quickly, and you want to help dampen that so you can actually allow the model to learn from itself. Or if you want to control the features which are dominating in the data set. So if you have too strong of a feature engineering. So that's why those are some reasons why you would do it. But in math terms, it's also called the Lagrangian multiplier, or a complexity control. So just for the sake of showing you guys how the model changes, I didn't change anything else, kept everything at the max step 3, 10 for the number of rounds, early stopping at 3, same objective. We have the same weighting, and then we have the gamma equals 1. So we ran that. If you notice, didn't really change too much. Actually, it's kind of stabilized it over here at the 7th iteration. So I kept it from really going too crazy and overfitting. So we'll do the prediction, we'll do the error, and then we'll print that. And then we notice over here that the test error is actually exactly the same. So 73929, 7392999. So it didn't really change anything over there. So after that, this is my attempt at creating the lowest error with all of the different parameters that we talked about. So the parameters that I chose were the max depth equals 5. So that means that there's 5 layers, or 5 places where it can where the decision tree can split from. We also have the number of rounds set to 15. So it'll run the model 15 times. It stops the model at 6. 6 if it doesn't improve much. The objective is the same, the scale. So I decided to keep the weighting in there because it is a rare event, and then I set the gamma equals to 2. So basically, there's no science to this, except for the fact that it's doing a lot of the science. But the cool thing is that you can plug and play, and you can keep doing it over and over again until you get something good to help the machine along. So if you notice over here, over time, over each iteration, as it gets to 15, the value actually gets lower, and then it actually gets the lowest on the iteration number 14, which is a good sign. And then after that, it actually errors out. The error starts increasing back up to that. So usually what you want to look for is some kind of U-shape whenever you're looking at that, and then this is exactly what you want to see. So this is pretty much the best that this model can get. And then after that, it comes back up, unless you were to tweak anything else, or you increase the max depth or anything like that. So we'll go through and we'll run the prediction on the test data set, calculate the error, and then we'll print the results. And then we actually had a 0.54%, which still is not better than the basic model that we had. So that's an important thing to note, is that the more simple your data set is, the less tuning you need to do, because there's really not that much depth that you need to have. So there's no point in actually going above and beyond for it if you have a smaller data set. By small, I mean by the number of columns. So if you had like 50 or 20 columns, then that's a completely different story, because there's so much more variation or different combinations that you can have for that. So speaking of that, wanted to start talking about examining the model outputs. So there's some additional things. There's a cool feature over here called xgb.plot multi.trees. So the cool thing about this is that if you run this, it should work. Let's go through, run this, run. So disregard that error down there. It's more of a warning. It's actually not an error sign. And then we'll go through and we'll zoom on this, and we'll notice that there is actually the tree, the graphical tree. So this is the top of the tree. So reviews. So the number of reviews is actually the most important factor. And then after that, reviews is again the most important factor. And then it breaks it up by the different values, which isn't actually these. These are the odds. So these are the log odds, which we'll go into a little bit further down, and I'll explain what those are. And then these are basically the different, the leaves are really what you should be looking at the end there to calculate what the values are. So from there, it'll just tell you what the most important features are. So if you want to take a look at the way this looks in terms of a data frame, so this is what that data looked like as it was running through all the information in the model. And then this is a function that we wrote to convert log odds to probabilities, so it's a little bit easier to see. And then so we wanted to see the size leaf, which is this value right here, so the 597,896. So we want to calculate what the probability is over here for this leaf. So let's go ahead and we'll take that and then plug that in over here. Copy it over, I think. So then the probability is 51%. So this leaf is 51% of this node right here. So this is the majority of that node right there. And then it'll break that off a little bit further. And then another cool thing is the importance matrix, which we'll plot as well. So we'll have the xgb.importance, we have the names, this is the original matrix, and then we have the model in there as well to help calculate the importances. And then from there, I'll create another one. So from here, we can see that the bigger this column is, the more important that value was, that field was. So reviews, again, the most important thing. Then its size, so the size of the file. So that means that if someone sees reviews and it's good and they realize that, oh, it's like 3 gigabytes, then they're not going to download that app. And then there's also the sentiment subjectivity, and then the sentiment polarity. So these two factors also played a role, but not quite as big as the number of reviews. So I think it's without really having to run this whole model, someone could probably tell you the same thing, that the more reviews something has, the more it's been vetted. And then if it has a high rating, then if there's a lot of people that are using it, then obviously it has something to do with the number of people that are installing the app. So if I were to be doing an app, running an app store or creating a new app, what I would do is I would try to get as many reviews as possible, because that is going to get me more installs and even more reviews, and that'll make me more money. Thank you.